Okay, by my clock, it's 12:30 Central Time. So welcome to today's webinar, Innovative Approaches in Phytopathometry, Epidemiology, and Microbiology, focus on corn tar spot. My name is Laura Isles. I'm one of the co-directors of the North Central IPM Center. We're one of 4 regional IPM centers supported by the USDA NIFA Crop Protection and Pest Management Regional Coordination Program. We have a mission to coordinate IPM across the region. Just a note during the webinar, if you do have questions, there's a Q&A part down at the bottom of your screen, and our speaker will answer questions after the webinar. So I'm happy to introduce Christian Cruz, who's from Purdue University, who's going to lead us off and introduce himself a little and then talk about his research in corn tar spot. So I'll give it to you, Christian.
Thank you, Laura, and thanks for the invitation. I'm honored to be here today. So the idea of the presentation is to share some of the things that we have been able to accomplish over the past few years. I recently moved from assistant to associate, so there's a lot to be discussed today. Unfortunately, we're limited with time, so I'll do my best to share as much as I can. So there are two aspects or two main interests in our lab. So on one side, we have the measurement science, or what we call phytopathometry. And so here we're dealing with different ways on how we can measure disease primarily. And so there are different methods. Visual assessments is the traditional one, but with the advent of technology, we have been using and leveraging the potential of imaging and other type of sensing technologies to acquire information and extract data from those files. And so obviously, in order to make sense of that data, statistics, data science become extremely important. Artificial intelligence and other methods are also implemented. And so ultimately, the goal is to use that information for epidemiological purposes. And so in our case, we focus primarily on 2 pathosystems. One is wheat blast, and the other one is tar spot of corn. Here I'm sharing a list of selected publications from my lab over the past few years. If you can take a quick look at the phytopathometry column, there are different publications. Some of them are associated with algorithms that we have developed to detect and quantify both wheat blast or tar spot of corn. And of course, we are interested in using other types of platforms to acquire information, mount optical sensors or other types of sensors, acquire information, and later extract that information and input them into the models. And so on the other side, we have epidemiology. 2 things that I wanted to highlight here is that we tend to collect information and try to characterize dynamics at the horizontal level, at the vertical level. In this case, we're showing different canopy levels of a plant, etc. But also try to go a little bit deeper and try to determine if we can have a much closer understanding on how the epidemics are developing. And I'll show a few examples about those. So just to jump in right away into some of the examples that I have for today. Wheat blast. So I started working with wheat blast back in 2009. And we've been working with this pathosystem ever since, even though it's not present in the US yet. It's present in South America, in South Asia, as well as in Africa, major disease over there. The main characteristic is that, so when growers report it, usually they do it at the heading time, as you can tell from this picture. And so unfortunately, that leaves a very short window for growers to react. And so I'll show you one example here from this publication. So in this case, when we started working with wheat blast, the status quo was that it was mainly a disease of spikes. And so even though we had that understanding, we decided to start quantifying disease early on, and also including the leaf. And so what we found here was that the leaf development is pretty much inconspicuous compared to the spike blast development. We have 3 different epidemics, 3 locations, same cultivar. But we also included a spatial description of what was going on in each of those locations. And so for the leaf blast development, you see that there's a continuation. So from day 41 after planting, all the way up to 74 in this case. Sometimes the epidemic is shorter because the intensity of the disease is so much that would kill completely the plants and the population of plants. And so, but here's perhaps a much better appreciation of what's happening at the spike level. And so this is unfortunately what the growers usually report. And this is what I mean by when the report comes to us or to the extension personnel in charge, things are pretty much too late. The growers only have just a few days before the entire epidemic starts to expand to entire fields, right? So our recommendation after this work was to start taking a look before even the spikes start to develop and look at those leaves. So on another manuscript that was also published fairly recently, we went a little bit deeper, and so we started to describe and first characterize and extract information from different canopies as the data were coming, and then start using Markov chain analysis to explain how those epidemics were developing. And so Markov chains are a bit complex to deploy in graphics, but what I wanted to share in here is that we were working in 3 locations, 3 different cultivars, each cultivar with a differential level of resistance. And so what we found, again, I guess that we reconfirmed that the epidemic actually was starting from the lower canopy. And then over time, it started to grow up and go up to the spike. And so again, the recommendation was to start looking at those lower leaves early enough and so make a decision as the epidemics start to develop and not necessarily only during the spike development. Something else that we started doing back in those days in parallel was to test with drones and see. We're talking about the year 2014 and 15, and so the idea was to see if there was any benefit in using imagery and later extracting information from those images and try to associate the data with the visual assessments that were conducted in parallel. And so there were 2 locations that we had used different time points. In this case, we only had 3 time points, but in a different location, we ended up having 5 time points. But what I wanted to share from this modeling perspective was that when a concordance analysis was conducted and we compared imaging with visual assessments, the trends were similar. They were not the same. So as you can tell, the data doesn't match exactly, but the trends are pretty much the same. And so we even went a step further and used population growth models to extract parameters and start comparing the parameters from those variables and see how they behaved over time. And so we thought that it was very promising to do this type of research and continue to do it as I started this position at Purdue, actually my previous position as an assistant professor at Purdue University. And so at Purdue, when I arrived here in 2018, tar spot had already been detected in the year 2015. And so I quickly had to make a decision on what pathosystem to put more emphasis on. And so we were fortunate to collaborate with people from the botany department and also from outside of the department. But the original idea was to continue to test some of those original work that we had started with BLAST. And we conducted similar research using drones and multispectral cameras, collected the information, extracted the data, also conducted concordance analysis to compare visual assessments with digital measurements. And so, long story short, the report from Song-Chang Oh from that manuscript was that the level of concordance was relatively good, except when the quality of the visual assessments were not sufficient to obtain those high levels of concordance. And so you can tell from that manuscript that in some cases we had high levels of concordance. In other cases, there's much more variation in the data sets, but mostly because of the visual assessments. So in this second manuscript by Chongyan Zhang, he went one step further, and besides conducting concordance analysis, he also used a population growth model, in this case, logistic, to compare and contrast the disease progress curves that were obtained by visual assessments and also from the digital information. And so from these disease progress curves, you can tell that, again, the trend is pretty much the same. However, we see large variations in some cases. And so for that reason, we started to rethink the way how we wanted to approach this type of research, because we wanted to go a little bit closer to a higher level of accuracy, which perhaps the drone information was not going to be able to provide. And so for that reason, we hired, at that time, we were very fortunate to hire Dr. Da-Yeon Lee. She was coming directly from the Ohio State University. And right away, she started working on this project that included the development of an algorithm that would extract information from proximal imagery. So in other words, images that were collected from the ground with high quality and high resolution RGB imagery. So there are two manuscripts that have been published out of Dr. Lee's work. And in addition to a provisional patent that has been obtained so far through Purdue. But so the objective here was to quantify, so detect and quantify tar spot stroma. And so the idea behind these goes to, or actually by two layers. So the first layer would be thresholding by using contour analysis of those stroma. And with the version 2 algorithm, we incorporated convolutional neural networks in order to train and retrain and basically continuously conduct those trainings of the model, because obviously there's always enough space for improvement. And so the algorithm has been tested under field conditions as well as greenhouse conditions. And so for field conditions, I wanted you to take a look at what we did here. So from microplot data collection, so we basically went to the field at these different times, collected visual information, but also collected imagery. And so we compared and contrast the data sets and the disease progress curves. So you can tell that there's a similar trend when you compare the visual assessments against the algorithm. But something important to notice is the scale. So when you're looking at the visual scale, you go from 0 to 50% in this case. When you're looking at stromata areas extracted by the algorithm, so it goes from 0 to 8%. And so, and this is through a different type of analysis that we conducted. So what happens here is that most of the time we observed that the visual raters tended to overestimate disease. And so in many cases, there was, even though we have prepared them with standard areas before the season started, even though by providing that information, in many cases, they were overestimating the disease intensity. So for greenhouse conditions, we also implemented the algorithm, extracted, in this case, not percentage area, but stromata count. And so keep in mind that a visual rater would take long times to do counts of these hundreds, if not thousands of counts in many cases. But so we decided to do these because not necessarily for the visual assessment, but that visual assessment was used as a baseline in order to train and test the algorithm. And so in this case, you see similar trends. However, initially we had detected that the algorithm was slightly overestimating the number of stromata, but ever since we have been retraining the algorithm and trying to achieve a higher level of accuracy, less bias, and more precision. So what have we learned from all of those experiments and projects? Definitely there is a strong reason, or there are strong reasons to modernize plant disease phenotyping. For those of you who have performed disease phenotyping in the field, you know that it takes time. It could be extremely expensive. So if you are dealing with larger fields, for example, you will have to rely on multiple people. And so slowly but surely things start to add up, and it could be a very costly endeavor. It's possible, but very costly. The overall research landscape indicates opportunities around AI and epidemiological modeling. There's actually a paper that we recently submitted in collaboration with several labs interested in this type of work, not only in the US, but also overseas. And also through collaborations and discussions with the industry within the US and outside of the US, we know that there are many opportunities around these areas of research. So although we have demonstrated the potential feasibility of using both airborne and ground-based phenotyping to quantify disease, there's definitely much more work to do. I would say that we're just scraping the surface. There's a lot that needs to be done in order to improve those models. So currently, my lab has 2 active projects. One is about to end, which is this first USDA NIFA project that we started in collaboration with Paul Isker, and also included the algorithms from Dr. Dayon Ni. I'm getting ready to start the report of that, but so it definitely includes some of the things that I just shared a few minutes ago. The second project that is still active is this NIFA project that started last year. It includes a component on microbiology. And so for this part, we are collaborating with researchers from Purdue and also from outside of the States, actually. And for the epidemiology part, the idea is to leverage some of those data sets that we have acquired that include visual assessments, weather data, drone information, the algorithms that we have developed, and of course, the models that we have leveraged in order to characterize tar spot under larger field conditions. So one of the ideas behind this USDA NIFA project is to explore methods to better train models. And so, in other words, use better training data. And in some cases, that training data comes from visual assessments. And the idea is to explore as much as possible in order to end up with high quality models that could later be deployed for digital information. And so in this example, I'm going to walk you through what we have done with one of my grad students, Brendan Lane. In the case of Brendan, his purpose is to characterize tar spot epidemics at larger scales. And so one of the first steps that he did was to lay out the field. In this case, we're using a 4-acre field. But in order to acquire visual information, he had to rely on 3 different radars. Something that we started to notice after a few preliminary runs of these heat maps, we noticed that at least one radar was consistently overestimating disease, and that was pretty clear. So what we had to do, and in the absence of methods that we could point out and rely on, we had to develop a method to normalize this information before we even start modeling anything. And so the model consisted on using different components of the concordance correlation coefficient developed by Linz back in the 90s. And so in order to acknowledge that there's variation, understand the sources of variation, the sources of bias, and then calibrate these different raters before we even start with the modeling component. So once that data has been normalized and calibrated, then we proceeded with the regular description of epidemics by using population growth models and disease progress curves. One thing that we oftentimes see in different tar spot reports is that it has an exponential phase, and we know that that's pretty common. But according to the data that we have analyzed from multiple years, we have seen that it really depends on the canopy that you're looking at. So in some cases, the lower leaves, although they develop disease, at some point they will die, they will senesce, and so no more disease will continue to increase. But the disease and the pathogens would start to move into the middle canopy and the upper canopies. And so you see an type of an S-shaped curve. So something else that Brendan decided to do was to use Markov chain analysis similarly to what we had done with the Whitlash system. And so in this case, Markov chains together with spatial analysis was powerful enough to indicate and tell us that even though the exponential phase is pretty obvious towards the end of the season, we definitely are able and capable of detecting disease pretty early in the season, as well, as you can tell from these spatial analysis. So there are different grades within that larger 4-acre field that started to show disease. And so we think that these may have implications on the way how people it can inform the growers. So obviously, so if you start detecting and start informing growers towards the end of the epidemic, that will probably give the grower only a few days to react. And in some cases, if the environmental conditions are conducive, maybe those recommendations will not be enough and sufficient to protect the crops. Some ongoing and preliminary projects include high throughput disease phenotyping using robotic platforms. We're in the process of analyzing some preliminary data and testing additional algorithms that we are developing in parallel. And something else that I also wanted to share briefly today is that this manuscript on the development of a reproducible protocol for Phylloxera matis inoculation in corn, it has been accepted with revisions. We're working on those revisions at the moment. The work included data that were collected both in the US and also in South America, in Ecuador, where tar spot is also a major problem. In parallel, we are also analyzing the environmental conditions that allowed for the development of disease on their greenhouse conditions. Keep in mind that greenhouses sometimes are not the best places to conduct these type of experiments because there's so much fluctuation. So it's not the same to do inoculations in the winter, for example, compared to the summer, when there's much more relative humidity in the air and when the conditions perhaps are more conducive for disease development. And with that, I wanted to acknowledge all the institutions and colleagues and collaborators who have helped us throughout the years and ensure that we move in the right direction with this type of research. And with that, thank you very much. I'll be more than happy to take any questions if there are comments or questions from people. Thank you.
Thank you so much. So yes, if anyone has questions, please type them into that Q&A portion at the bottom of your Zoom screen. So as people are typing in questions, I'll ask, what are the latest image-based methods developed for accurately measuring the severity of tar spot disease in corn?
Yeah, for tar spot, there are methods, there are ground-based methods, there are airborne-based methods that include image processing. And now it depends on the type of image that we're dealing with. So those images can be multispectral, could be RGB. By the way, we're not the only lab that has developed methods. So I know that there's at least another lab in Mexico that has been working on these type of methods.
Again, type any questions that you have there in that Q&A portion. So how do tar spot dynamics observed in field conditions combined with like the near real-time data you're getting? Do you think that's going to encourage farmers to rethink disease management strategies?
Yeah, that's a good question. So let me go back to this slide. So although this output is based on visual information, so this is telling us that even visually we can detect things way before the average, right? Usually the average is you have to wait until the VTR state and then start looking right after that. But so based on these outputs, we think that we could perhaps rethink the way how we collect information, how we do phenotyping. Perhaps technology can help us, right? Definitely a single human being won't be able to acquire all this information that we have here, but maybe machines.
They could get to the point where you could visually tell when maybe a fungicide application would be beneficial or not before it's too late, or is that?
Yes, exactly. It's possible. Sometimes remember that that you have to combine these with environmental conditions because they are part of the disease triangle. So
Exciting time. I know you mentioned, inoculation kind of there at the end of your presentation, depending on conditions. So how feasible is it to successfully inoculate tar spot under semi-controlled environments? I know that's a hard part of pathology research, is getting the disease.
Right, absolutely. So interestingly, we had much success in Ecuador than what we had in the US, at least for the data set that we published. We're trying to publish in this manuscript, but with success, so we have been conducting additional inoculations ever since, and we have learned a lot. And so it all depends on the environmental conditions. If you are not careful enough to provide standard conditions, then it might be a 50-50 chance, right? But so far, we are achieving 100% success with high levels of severity. So it's possible.
That's really good.
Yeah.
I mean, not good for the plants, but good for disease researchers.
The research, yes, absolutely.
Very good. So I'm not seeing any other questions pop into our chat. I do see Kelsey Mueller has dropped into the chat links to your lab and so how to get in touch with you. So thank you again. Again, Dr. Christian Cruz at Purdue University doing some great research on tar spot. So anyone who's listening wants to connect, you have those links there and how to connect up to you and get in touch with you for any other details. Our next Pest in Progress webinar will be February 19th, 2025, again at 12:30 Central Time. And at that time, we'll have Caitlin Rearing from USDA ARS talking about pollinator-safe fungicides on the floromicrobial biocontrol of anthracnose and blueberry. So we'll hopefully see everyone in about a month. And thank you again, Dr. Cruz, and everyone have a great rest of your day.
Thank you very much.